want to donate, there is a link on our website to email us to donate. Right now, we just, like I said, have a bank account, so you can just do Hurikomi or a bank transfer. But soon, hopefully, this will be easier and less painful if you do wish to donate. We also are always looking for an online community lead. So right now, we record these sessions, and then I edit them and upload them as best I can, but it's kind of not my bag. You know, it's like I just do that on the side. So they're not that great, and I don't have time to manage the channel and do any kind of like engagement on LinkedIn and all this stuff. Mate and I try and split that, but it's, you know, we got other stuff going on and we're not really good at it. So I'm good enough to know my weaknesses. So if anyone is interested in that and has experience in it, we would love to have your help. We'll find some way to compensate you or highlight you in some way that we can. So if you're interested, please come speak to me. And if you work anywhere that might want to sponsor us, or you yourself want to, and if you'd like to help volunteer, today we had some people helping hand out the badges. Like I said, there's some stuff in the works that'll be bigger, and we'll need more volunteers for that. If you want to be involved, let me know. And with that, this is Alex. Alex is going to be talking to us about saturating the NIC. It is an insanely interesting talk. I did not expect it to be so ridiculously fascinating. So I will just leave it at that. One more thing, special thanks to the Google for Startups staff, the security, our friends at the desk, and Sunshine for helping us and letting us use this space. And I've talked enough now. So I was just mostly trying to kill time for more people to show up, and nobody did. So anyway, we'll chat more at the end of the talk. So
all right, thank you, Brandon. Expectations set. Today we're going to be talking about high-performance network programming. The hardware you can buy these days is capable of amazing throughput. But writing software which keeps the hardware fed is actually kind of tricky. Fortunately, Linux and Rust give us some tools we can use to make the most out of our precious hardware. And we're going to look at a bunch of those tools today. But first, I want to talk about Blue Sky. I guess most people know what it is. In case anyone doesn't, it's a Twitter, like X or Threads or Mastodon. It's one of those. Personally, I'm not a Twitter connoisseur, so I have no opinions about which is the best. But from a programmer's perspective, Blue Sky does have a nice property, which is that all of the data is publicly available, which means we can play with it. In fact, the data model, I was reading about how it works. It's kind of interesting. It's kind of a return to the past. So before microblogging, we had blogging. And the way that works is very simple. You upload your blog to your server or someone else with an RSS feed. And if someone wants to subscribe to your blog, they throw the link to the RSS feed into their feed aggregator. And then every time they click the refresh button, it will poll all of the RSS feeds to check for any new posts that have been uploaded since the last time it did a poll. So that you know, the good old days, that worked great. There's no fundamental reason why the same model can't also work for microblogging. The only difference is scale. So Twitter users expect to see new posts like a second after they've been uploaded. And popular accounts could have hundreds of thousands of followers. And if you have 100,000 feed aggregators polling your RSS feed at a frequency of once a second, your server is not going to be very happy. But it turns out that the thing that was missing from the old RSS model was push notifications. So here's Blue Sky's idea. Instead of having everyone polling everyone all the time, you have a single big scraper machine somewhere in the cloud, which polls everyone's RSS feeds. And every time it discovers something new, it emits an event in this feed that it calls the fire hose. And then downstream consumers take that fire hose and filter it down to just the accounts that you're interested in. So here's one of the URLs that they advertise for the fire hose. So let's have a look at it. Yeah, so WS scheme, so that means it's WebSockets. WSS is just the TLS encrypted version. So I'm going to throw it into WebSocket, typing with one hand, which is like Netcat, but for WebSockets. And there we go. That's the Blue Sky fire hose. So every time anyone does anything on Blue Sky, you get a line in this feed. So we can see, let's see, someone creating a repost, someone creating a like, deleting a follow. Yeah, so basically any change to the state of the entire Blue Sky network is represented with a diff in here, in JSON, obviously. We can take a look at how much data is going through here. Looks like it's currently about 140 kilobytes per second, 160. Obviously, it fluctuates a lot, especially depending on the time of day. But typically, I see about 400 messages per second, and with an average size of half a kilobyte per message. So that's a data rate of 1.6 megabits, or about 16 gigs a day. So it's not like crazy huge data, but it's not nothing. Yeah, and notice that this URI that we connected to, it says US West in there. This is not the big machine. We're not connecting directly to that. Instead, that relay that's doing all the scraping distributes the fire hose to a number of geographically distributed repeaters, and then clients like us connect to our nearest repeater, which makes sense, right? Like if you have 1,000 people in Japan who want to follow the fire hose, it doesn't make sense for all of that data to cross the Pacific 1,000 times. You just set up a node in Japan and everyone connects to that. So our project this evening is going to be to implement one of these. It's a pretty simple program. It connects to an upstream fire hose provider, and it accepts connections from clients. And every time a new message arrives from the upstream fire hose, we just repeat it to all of our clients. I'm going to show you 4 different implementations of this. There's going to be a lot of code. But if you follow along to the end, the payoff is you'll know how to write software which achieves pretty high throughput. If anyone has any questions or doesn't understand some of the code that I'm showing, please do ask, because if you get lost, it's better to recover quickly. And if you have any criticisms of my code, I want to hear that as well. Okay, so off we go.
If you do have a question, just raise your hand, and if I don't see, like, just get somebody to get my attention, and I'll give you the mic so that the recording can pick it up and that we can hear. So
great. Okay, so our first Blue Sky repeater. So it's WebSockets, right? So I went to crates.io and I searched for WebSockets, and it looks like the most popular crate is this thing called Tungstenite. It seems pretty good. Basically, it exposes 2 functions. One for when you're the client and you want to connect to a WebSocket server, and the other one for when you're the server and you want to accept a connection from a client. Both of these, they just do the WebSockets handshake, but in different directions. And they both return a handle which implements stream and sync. Stream is like the async version of iterator, and sync is the async version of extend, I guess. And it's async, so that means we need an async runtime. I'm just going to use Tokyo. And I noticed that Tokyo has this thing called broadcast channel. It gives you a send handle, and you can make a bunch of receive handles. And anything that you send to the send handle gets received by all of the receive handles. So perfect. This sounds like exactly what we want, right? So all we need, oh yeah, I wanted to just dig in a bit on how the broadcast channel works for a second. So internally, it's a double-ended queue. It's a ring buffer, and when you send items with the send handle, it pushes them onto the queue. So send, 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 and then each receive handle has a cursor pointing somewhere into this queue, right? And the cursor points to the last message which that receive handle received. So if C2 calls receive, it will receive a clone of this first item, and its cursor will advance. Receive, receive, receive. Furthermore, if you call receive and you're the furthest person back, like C1 here, when that calls receive, we can also drop the data because C1 was the only one that was waiting for it. Receive, receive. Okay, so I think that's, seems like a good implementation. Makes sense. Let's just wire this stuff together. Okay, so at the top, first thing we do, bind a socket. That's for our clients to connect to. Next, we connect to the upstream fire hose. That's just the URL we were looking at earlier, and create one of these broadcast channels. In the task on the left, we're waiting for messages to arrive from upstream, and then we send them to the channel. And then over here, we're waiting for clients to connect. Whenever a client connects, we create a clone of the receive handle and spawn a new task. And then we do the WebSockets handshake with the client. And then every time we get a new message from the channel, we send it to the client. Does that make sense? Any questions about that? Okay, yeah, simple. How does it do? Oh, yeah, so I'm benchmarking it by firing up a copy of this on one machine, and then from another machine, I'm just connecting more and more clients to it until it falls over. And in this case, it fell over with a too many open files error. Turns out there's a limit to the number of file descriptors you can have, and every socket consumes a file descriptor, so we need to raise the limit. A couple of ways of doing it. I'm going to do it with systemd. Let's try it again. Okay, so I kept connecting clients to the server until it fell over, and that happened at like around 2.8 thousand clients. And I saw a maximum throughput of 4 gigabits. So is that any good? It's okay, given how straightforward the implementation was, I think. I mean, this took no time to write. And if you have a 1 gig NIC, then you've already saturated it. If you've got a 10 gig NIC, like most servers, then yeah, you're leaving half of your performance on the table, but maybe that's okay. But as the question mark boxes would indicate, we can do better. The first step to optimization is understanding. So we're implementing WebSockets here. So let's find out how WebSockets work. I didn't know, so I went and had a look at the RFC. It's very short and understandable. Basically, it's a TCP-based protocol. So the client opens a TCP connection to the server, and then we do a quick handshake. The client sends some headers, starts out pretending that it's speaking HTTP, and then immediately admits that it's not, and then sends some random bytes. The server replies by saying, okay, let's speak WebSockets, and here's a hash of your random bytes, just to prove that I was paying attention. And then after that, it can start sending messages, which look like this. So you can send any payload you like, and you prefix it with essentially just the length of the payload in some variant encoding. So it's really an extremely simple protocol. Right, but here is our first opportunity, because this is WebSockets appears to be a message-based protocol, but really it's TCP. It's just a stream of bytes. We've been sending one message at a time, right? We've been doing one send that goes up to the exclamation mark, and then we do another send for the next bit. But there's nothing that says we have to send, our sends have to be aligned to the message boundary. You could send some like random chunk and then another chunk. You could send multiple messages in one big chunk. So if we batch up the messages are coming in from upstream at 400 Hertz. If we send them, for example, in batches of 100, then instead of doing 400 half kilobyte writes, we can do 4 50 kilobyte writes. This is going to be a lot more efficient. Not only because it's just fewer syscalls, so less syscall overhead, but also the Linux TCP stack gets more efficient as you push bigger chunks of data into it. Like the objective really should be to fill up the send queue. That will optimize the efficiency of the TCP stack. It just gives Linux more opportunities for how to packetize the data. There is a cost to chunking up the messages. So if we were to chunk them up into batches of 100 and send them 4 times a second, then we're adding, 100 millis of latency on average. I think that's probably fine in this case. No one's going to notice. So here's our second implementation. Starts out the same, bind the sockets, connect to the upstream. Now, instead of using a broadcast channel, this time I'm going to shove everything into a giant vec of bytes. So if we look at this task here, message arrives from upstream, we add the WebSocket framing bytes, and then push it onto the vec. So that means this vector is going to contain like the literal byte stream that clients are expecting to receive over TCP. So now over here, when a client connects, we spawn a new task. We do the handshake, but I'm not going to use the sync thing that Tungstenite returns anymore. I'm just using it to do the handshake. After this, we're going to use the raw TCP socket directly. We now need to keep a bit of state for each client, this offset. This is going to be an offset into the vec, which just shows which byte, up to which byte has this client read already. So we'll initialize that to the current length of the vec. And now in a loop, the new data is going to be everything from the client's offsets to the end of the vec. That's the stuff that's in the vec that the client hasn't received yet. So we just send that to the client's socket, and then however many bytes we manage to send, we'll bump the offset by that. You may have noticed I've also got a semaphore going on here, this notify thing. This is just so that, imagine if we weren't writing anything to the vec, this loop here would then just like busy loop with like an empty slice every time. So to prevent that, every time round the loop, we wait on the semaphore, and then every time we push to the vec, we notify the semaphore, which then wakes up everyone who was asleep. Okay, any questions about that?
Yeah, we got a question.
So is any of the data dropped here?
Yes, you've noticed that this vec is going to grow and grow and grow until we run out of memory. Yeah, I guess in a real implementation, you would use like a vec deck or something. I've chosen just to allow my machine to Hold on.
Looks like we got one more. I'm coming.
I actually have two questions. So one of them is, so I guess I'm trying to understand is, does this solve our issue of having too many, I guess like WebSocket handles open, or have we not gotten to that yet?
Oh, I solved that issue by raising the file descriptor limit. So
nice.
yeah, I set the limit to infinity.
Oh, that's
So
right.
we don't
that's
have
right,
any
yeah.
issues anymore.
Thank you. Thank you so much. And then also, I guess like how is what you're doing here different than what Toke.io is doing internally with the with like broadcasting messages?
Yeah, with the previous implementation.
Yeah.
Okay, so the previous one was every time a message came from upstream, so 400 times a second, we would receive the message,
Mhm.
add the framing bytes
Mhm.
for every client, and then do a send. Right, okay. I think your question is, where is the batching here?
Oh, yeah,
This
yeah.
is a good question. The batching happens implicitly. So imagine if if we've got a lot of clients connected and it's running slow, then by the time you come around the loop in one client's task,
Mhm.
probably multiple messages will have been pushed to the VEC,
Mhm.
and they all get sent in a single batch. So
Okay.
every time we come around to this point, we send to the client everything which it hasn't received yet, which may be one message if everything is keeping up, or it may be a ton of messages. Like if we get round to here again and the client's offset is 2 megs behind the end of the VEC, we're going to send one giant 2 megabyte chunk, which the kernel will then efficiently send to the client.
Oh, I see. So the reason we stopped using I think it was the broadcast function is just because we need to do this batching internally.
Yes, the broadcast thing was forcing us to do one message at a time.
That makes sense. Thank you so much.
So just to be clear, like what you're saying is that the more load we have, the more we're going to be batching like automatically.
Exactly, yeah. So if we're completely fine and we're keeping up with the clients are keeping up, then it is just going to be sending every message, one message at a time, just half a kilobyte at a time. But the more under load we get, the longer it's going to take to get for the client tasks to wake up again, and the bigger the batches are going to be. So, in fact, that's what the next slide is about.
So one more, actually. It looks like two more.
Oh, yeah.
Sorry, is there anything stopping us using the broadcast queue, but instead of putting a single message into it, just put everything into it? I guess maybe the library doesn't support just reading anything other than a single message at a time.
Okay, I guess you're saying, if we had the old implementation with the broadcast channel, when we come around the loop, could we then like take out everything that's waiting in the broadcast channel for this client,
Yes.
stick them together, and then submit
right.
that to the kernel as a
just-
single write? Are we
I
good?
Yeah.
But I mean, it involves a little bit of like some mem copies.
I just realized the broadcast thing has to be like delimited by item. That's the
Yes,
problem there.
unless you're sending 1 byte at a time into
Yeah,
the broadcast channel.
Okay, thank you.
Yeah. Yeah. So this is a property you really want your networked app software to have, that it gets more efficient as it comes under load. Some software out there has the opposite problem, where it runs very efficiently until it really needs to be running efficiently, and then for some reason, the efficiency goes off a cliff. You usually hear about that kind of stuff in blog posts written by SREs who have just had a traumatic experience. But this does the right thing. It gets more efficient as it comes under load. And the performance? We've run out of IP address port tuples. This one's a global limit, so we have to use sysctl to raise it. Okay, with that done. Yeah, so this works a lot better. I was surprised by how effective this optimization was. It does also have the side effect of making benchmarking a little bit harder, because previously I was just standing up the server and then connecting more and more clients to it until it fell over. But the new server, Impl 2, doesn't fall over so much as you get like a smooth degradation of quality. Like as you connect more and more clients to it, the feed the clients receive starts to get sort of jumpier and jumpier. Like they start receiving messages in huge batches. And at some point, the clients are receiving like nothing for multiple seconds, and then multiple seconds worth of messages just appear. I wouldn't say that that is succeeding in keeping those clients fed. So I made a kind of judgment as to how many clients it was properly able to handle. But at 15K, those 15,000 clients were receiving the feed with like 1 second or less of latency. So I think it was really handling them. And the peak throughput I saw was 32 gigs. These numbers don't exactly match because the peak throughput is what you see when you really overload it. Like this is the maximum amount of data that it was able to actually drive. But that was not a good experience for the clients that were receiving it. Okay, can we do better? At this point, if you profile it, you'll find that pretty much all the time is being spent in the write syscall. We're just doing a ton of writes. A little bit of time spent locking the mutex. So what's going on when we write to a TCP socket? Every TCP socket has a send queue. And when you write to the socket, it pushes data to the back of the queue. And then at some point, data at the front of the queue is going to get packetized and sent off to the network. Even later, when the person on the other end of the socket acknowledges receipt, we can drop the data from the front of the queue. Yeah. So the send queue is normally the bytes are not stored inline in the queue. Instead, the queue is a queue of references, ref counted slices, basically. If anyone knows the bytes crate, it works pretty much exactly like how bytes does. But yeah, the point is that these queues can store references to data stored elsewhere. So we pass a slice to write. You might think that that slice then gets pushed onto the send queue. But yeah, that is not what happens. And if you think about it, that wouldn't work. The reason is that write returns as soon as the data is in the send queue. But these references, the memory that these are pointing to has to remain valid until the data is gone from the send queue. And from user space, you have no way of knowing whether that has happened or not. You write data to a socket. At some point later, that data is going to be acknowledged and dropped, but you don't know when that's going to happen. So if a reference to your user space memory ended up in one of these TCP send queues, you would never know when it was free to when it was safe to free that memory or use it for something else. So what does the kernel do? It does a copy, of course. When you call write, so here we're writing a chunk of data from the end of our big vec into this socket send queue. First thing that happens when you call write is it grabs the nearest bump arena. It has a few of these bump arenas, copies the data into there, and then pushes a reference to that copy onto the socket send queue. At this point, this is safe because the kernel can manage this reference holds a ref count on the whole arena, so it's not going to get freed until all of the references pointing to it are gone. But look, if we've got 1,000 clients connected and a new message arrives from the upstream firehose, we're gonna send that exact same data to all 1,000 clients. We're gonna call write in a loop, and every time it's gonna copy the same data again and again and again into this bump arena. This is painful to look at, right? What we want is this. We want to copy the data once and then push references to that data into the send queues of all of our clients. Sadly, no such syscall exists. It's kind of like the inverse of a vectorized write, if you think about it. But we can maybe convince the kernel to do this anyway. What we need is some kind of buffer in kernel space, some buffer that the kernel controls, which means that the kernel will be happy to create references from it, that's long-lived enough for us to use it as the source of multiple writes. So this sounds like a memfd. So a memfd is exactly, it's a kernel-owned buffer that you can manipulate from user space. You get a file descriptor that points to it. Here's how you create it. You call memfd create, you give a label. I was initially confused about what this label was. It's not like this is has a path on the file system or anything like that. You can make multiple memfds that have the exact same label, so it's not an ID. I found out what this is for though. You might know that if you list /proc PID/FD, you can see all the file descriptors that process has open. And if you do ls-l, you see that they are symlinks. So here you can see standard in, standard out, standard error are connected to my terminal, which I guess is PTS10, apparently. So that makes sense. But FD3, which is this memfd, is a symlink to /memfd : blah, blah, blah. And I'm pretty sure this file doesn't exist. So what's up with this broken symlink? Turns out these are not symlinks. procfs is a liar. What this actually is that the kernel has some diagnostic information that it wants to tell you as the user of the computer. And the way it's figured out to get this information to you is by pretending that and stashing this freeform human readable stuff in the symlink target field so that ls can show it to you. This is a user interface, possibly the hackiest user interface I've ever seen. But I kind of love it. Okay, so that's how you make a memfd. Here's how you can append to it, you can modify it, resize it. And you might be looking at this API, I think write, mmap, ftruncate. This is the file API. Yes, it is. A memfd is just a file that has nowhere to do write back to. It lives in the page cache, but there is nowhere on disk for it to synchronize its changes back to. So it's just permanently dirty. It's actually the same thing that happens if you open a file in a tempfs. And like any other file, we can use sendFile. So there's a syscall called sendFile, which lets us send a chunk of a file to a socket. So when we call sendFile with our memfd, the kernel, because this is kernel-controlled memory, it will just push a reference into the send queue. Reference pointing directly into the page cache. Very fast. Very cool. So here's our third implementation. Start the same. Bind the socket. Connect to the upstream. Instead of a giant vec, I'm now creating a memfd. And now in the upstream task, whenever a new message comes in, we add the framing bytes and append it to the memfd. Over here, client connects, we do the handshake, initialize the offset, and right here we are calling sendFile. We're just writing from the memfd into the client's TCP socket, starting at the client's current offset, length, just a big chunk, but it'll go to the end of the file. It won't like go beyond the end or anything. And sendFile will actually update the offset for us with however many bytes actually get sent. You might notice that I've had to wrap sendFile in this async IO thing. This is just because sendFile is just the raw syscall. It doesn't know about Tokyo. So this is the way how you bridge syscalls with the Tokyo reactor. And by the way, I'm getting sendFile here from the Rustix crate, which is just a fantastic crate. If you ever find yourself reaching for NICs or libc, Rustix is just a really high quality implementation of the same kind of thing. Yes.
What's a Tokyo reactor
Uh,
at a high level? Just in case.
the heart of the Tokyo runtime system. So basically it's keeping track of sockets which we're waiting for some kind of event on for them to become readable or writable, and it's keeping track of futures which it needs to wake up and retry when that happens. It's a fancy way of using EPOL. Yes. Oh, microphone.
And what happens? Can you show the diagram again with BAMFD?
This one?
So if we have, for example, one client is very slow,
Yep.
and it has reference to one of MEMFDs, so one client will stop cleaning up of MEMFD for all the clients.
So as in the previous implementation, I'm not doing any cleanup at all at the moment. But if you did want to do cleanup, the way you do it with MEMFD is with something called hole punching. So this is there's a syscall which lets you blast a hole in a file, and this also works with MEMFDs. Just replaces that whole region with zeros and drops all the pages associated with that region, so it no longer uses up any memory. So if we were doing cleanup properly, we would have another task which just once data starts getting too old, we hole punch it and just like drop it from the MEMFD. If the client were to wake up from its long slumber and suddenly start trading its send queue at that point, it would receive zeros. But yeah, I think there's no problem where something's going to prevent us from freeing memory. Okay. So let's see how it does then. It's a big uplift, yeah. And I mean, this is really keeping 48,000 clients properly fed, like with low latency. Yeah, and again, for like kind of a 2-line change again. And this is just to show our software is now just spending all of its time in sendFile. Like the bit of this flame graph which is not sendFile is this thing over here. Caveats about sendFile. I think sendFile is great and everyone should use it. It's kind of portable. The FreeBSD has it, macOS has it. OpenBSD does not. You should know that if you open like a 10 gig file and then you sendFile the whole thing to some client, the memory for that file is locked in the page cache until the client reads it all. Yeah, unless you whole bunch the memory away. Anyway, this is the big one. If you send a region of a file to someone, and then you modify that region of that file using just pwrite or mmap or whatever, you have no way of knowing whether the client is going to see the old data or the new data or some mix. It's not specified. So basically, once you've done send file on some bit of a file, you should, I think, treat it as immutable. But that's what our implementation does anyway, so that's good. There are a couple of other options for doing zero-copy networking. I'm not going to go into them. Okay, so can we do better? Like I said, so we're now spending all of our time doing send file. Send file is way faster than write because it doesn't have to copy any data. It's just pushing a reference onto a queue. But syscalls still have some overhead. Even if a syscall does nothing at all, it takes some time, mostly due to Spectre mitigations, which is sad. But yeah, so we're currently, for each client, we're saying, send file, kernel says, okay, we do the next send file, it says error or whatever, do the next send file. But suppose, we have a bunch of clients connected and a new message comes in and we want to send that message to all of them. We know we're going to do this whole bunch of send files. It's not like these depend on each other. So wouldn't it be nice if we could somehow batch up these syscalls, or you make some description of a bunch of syscalls and then submit that to the kernel as a single syscall, and then get back all of the results? That would that would bring the number of syscalls we're doing down from order number of clients down to order one, well, order number of messages or something. So yes, as you may have guessed, there's something that kind of lets you do this. It's called IOUing. You set up IOUing and you get a couple of channels, essentially. One is called the SQ, and that lets you send descriptions of IO operations to the kernel. And the other channel is coming back from the kernel to user space, and that gives you the results of those operations. Here's how it looks in Rust. I'm using the IOUring crate, by the way. So you push a bunch of descriptions of operations into the submission queue. These pushes are very fast. And now when you're ready, you call submit and wait. This is the syscall. At this point, we enter the kernel, and the kernel takes a look in the submission queue and loops over everything that it finds there and runs them one after the next. And instead of returning the results, it just pushes the results onto the completion queue. When it's finished, we return. And now from user space, we can take a look in the completion queue to see what happened. So that's how IOUing works. Over the last number of years, they've been adding more and more syscalls, more and more support for different syscalls to IOUing. And at this point, most syscalls have a corresponding opcode that you can use with IOUing, but not sendfile. It turns out the way Uring wants you to do zero-copy sends is with something called send zero-copy, which works just like a normal write. But remember, I said that the reason that a normal write syscall can't directly push a reference to user space memory to the send queue is because from user space, you'd have no way of knowing when it was safe to free that memory. Well, IOUing, there's no problem with having multiple completions from a single IO. So if you push a send ZC, you get back 2 completions on the completion queue, one when it enters the send queue and one when it leaves. And that tells you that the memory is safe to reuse. Okay, right. So let's see how it goes. Previously, right, okay. We can no longer use async Rust at all. It doesn't interact with Tokyo in any way. So we're now just doing normal synchronous Rust. And whereas previously we were having to store, previously we were storing the threads, the per client state, the offset in its task. Now we're going to have to store that explicitly in a slab. Okay, so I've gone back to having a giant vec of bytes. I've got a slab for storing client state in. Bind the socket, connect to upstream, initialize IOU ring. This is the same as before. This thread, every message that comes in, we push it to the vec. Whenever a client connects, we do the handshake and we insert something into the slab.
What's a slab, Alex?
A slab is it's so you can think of it like a vec of option of t. So it's like if you want to store state by just your first thought might be, oh, I'll just have a vec and every new client that connects, I'll push to the end of the vec. But then clients that disconnect, you want to remove them from the vec without changing all the indices. So if you have a vec of options, you can just replace it with none. But that has the problem that now your vec just keeps on growing and growing and growing forever. Even if you've got clients connecting, disconnecting, you end up with like a ton of nones followed by your clients that are alive. So a slab, instead of just having nothing in the gaps, it keeps a free list. And when you push, it finds the first empty, or it finds an empty slot to push to. Okay, yes, Mate.
Is this slab the same as a slot map? If you're familiar with that.
Yeah, I
Craig?
think it is the same as a slot map.
Thank
It's
you.
just yeah.
A slot map solves the ABA problem additionally, and I think a slab doesn't give you a handle. So slab just
Oh.
stores them as an iteratable, right? So
Does slot map have like a generation counter or something?
that's right.
Okay.
I secretly knew the whole time.
Slab is a primitive version of slot map. Okay, so here is the main run loop then. Okay, this is where the action is. For every client in the slab, if the offset is behind the head of the vector, i.e. there is data to push, then we submit a send ZC operation. We push it to the submission queue. And I'm going to attach the client's ID as a cookie. And I set client.inflight to true so that we don't submit multiple of these while the first one is in flight. We're going to do this for every client. And after having pushed maybe thousands of operations to the submission queue, we finally call submit at wait, at which point we go to the kernel. It plows through all of those IOs that we've submitted and then comes back. We go through the completion queue. We retrieve the cookie, which gives us the client ID, look up the client in this lab, and the result of a send ZC operation is the number of bytes that it managed to send. So we use that to bump the client's offset and set in flight to false. So that's how it works.
Can we see the first slide again really quick? And okay, so this is a separate thread from the loop.
Yes.
Okay.
So there are three threads running now.
Okay, they're each threads. Great. Got it.
Okay. How does it do? Poorly. Yeah. So disappointing. What's going on? Does IOU ring suck? I mean, it's really hyped. Is it just hype? No, it turns out IOU ring doesn't suck, but you have to fiddle with it a lot. I spent ages fiddling with this thing, trying to make it go fast, and I managed it. but it took a lot of fiddling. I'm going to just blast through these because I think no one cares. I barely care. You have to set these magic flags. Why are they not the default? You can register your file descriptors with the ring, which makes them go faster. You can register regions of user space memory with the ring, which makes any operations which access that memory go faster. This is all horribly unsafe. This is why, by the way, you may have noticed I'm allocating a 16 gig VEC and then making sure it never gets reallocated on pain of crashing. If you do these things, then you get another error. Turns out, yeah, using senzc and pinning the registering a 16 gig VEC use a lot of locked memory, which is another thing that Linux doesn't want you to use too much of. So we tell it to let us use it anyway. And finally,
Oh my goodness.
Actually, at this point, didn't you consider to do the opposite, like moving TCP stack into user space?
oh, you're talking about kernel bypass. Kernel bypass requires fancy hardware. Like you can't do it with a normal NIC. You need like a expensive solar flare. Were you talking about something else? Like
Oh, that's
FTP?
as far as I remember, there were two smaller projects. You're talking about that Facebook one, which is for data centers, but there were some cheaper options as far as I remember.
Okay. I don't know about cheap kernel bypass. Last time we investigated it, we ended up shelling out for a really expensive network card. Maybe we just got scammed. I'm not sure.
I was gonna ask this earlier. What sort of machine did you run this on?
Right. Okay. Yes. The benchmarks. I have rented a bunch of machines from Amazon with 300 gigabit NICs. Yeah. I didn't even realize that such NICs existed, but they do, and Amazon will rent them to you for not even that much money. If you have money, Amazon will do you a machine with a network interface measured in terabits. It must just be all network cards. Yeah. Right. The unholy abomination. So technically, I have not saturated the NIC of the machine that this is running on, but that's only because I rented such an overpowered machine.
You might be about to answer this, but what's the bottleneck here?
On IOU ring, yes, I can answer this. If anyone was paying very close attention to this massive code dump, they may have noticed that this is essentially a single-threaded program. Like all of the action is happening in this one loop, which is running on one thread. And you can have multiple rings, multiple threads running multiple rings. We could distribute the clients to different threads. I think it would probably be possible to improve the performance by multiple times using that over, oh, no, not over that, over the good one, yes. But I didn't do that.
Okay, one more.
About the offset, it keep incrementing. So in the steady state, like, can you keep running this for a while, or is it going to be like out of
Yeah.
memory at some point?
Well, this implementation, the answer is no, because this vector is we're gonna crash as soon as we write more than 16 gigs, which is like 24 hours of firehose, right? So we would have to have some better approach. But I think it's probably not too hard to make it work. It would just be more code than would fit on a slide. So instead of the vec, you would have like a vec deck, and then you'd want to maintain like a sort of base offset for the vec deck, so that you can reinterpret the client offsets. Yeah. Okay, yeah, caveats for IOU ring. Not portable at all, not even to slightly old versions of Linux. So, that said, I think, being brazenly platform specific is not that bad. If you are writing software for yourself, you know where it's going to run. You can just optimize specifically for that platform. Managing the lifetimes of these buffers is a real pain. Like when you submit something to the submission queue, which contains pointers to user space memory, the lifetime kind of disappears down the channel, and it's gone as far as rustc can tell. But then when you get the completion, it's back again. And that's the point at which you can then free the memory. Basically, rustc can't help you at all like you're used to, and you have to do everything by hand, manually, at runtime. It's a pain. And finally, you can't use async Rust anymore. So if you are writing complicated apps directly using IOU ring, you'll find yourself basically writing a state machine explicitly with like numbering all of the state transitions and then using those as your cookies. It's ugly. It's like using Mio back in the before Tokyo times. Okay, yeah, how can we make it faster? More threads, more rings, maybe kernel bypass, but I think actually probably kernel bypass is not that much faster than just using IOU ring these days. I think IOU ring has done a number for Solarflare's value proposition. Yeah. And I guess to recap, the first version was nice and easy. Adding a bit of batching required us to drop down from the WebSockets level to the TCP level, but we got a big uplift from it. Going a bit further, using some like kernel fanciness and sendfile, another big optimization. But again, just sort of a couple of lines change. We didn't have to re-architecture our software. Going full async with IOU ring required a complete redesign and a lot of hair pulling. It is just way worse, way easier to have bugs in your code. I wouldn't go there unless I had to. And most network software I've written has closer to the order of 10 simultaneous connections than 10,000. And so most of the time, doing the easy thing is the best, because software that does a lot of network I/O, it's hard to test. So you just want the code to be straightforward and don't give the bugs any opportunity to get in. But if you need it, now you know that it is possible to achieve incredible throughput from a single machine, and in this case, from a single core. I think probably, I don't know how many people are connecting to the Blue Sky Firehose. I'm guessing it's probably not more than 70K. So they could really run it all from just one machine if they were willing to put in the effort. Okay, and that's it. Thank you.
You're not free yet. I have some questions for you. But before I ask, does anyone have any other questions about the talk? I want to give the opportunity to...
Thank you for amazing, very complicated stuff. So the number 4, the optimization, uses a lot of syscalls, and you told you use unsafe Rust.
Yes.
Do you still think
Is there any benefit of using Rust for that
Oh.
level of?
Rather than C? Okay,
Um,
that's an interesting question. Yeah, and if you use C, then you even get to use like the official IO library. Which I mean, the Rust IO crate is not bad, and I think it re-implements a lot of the stuff from the official C library. So it's not like you lose out on, you're not doing everything from scratch. But I would personally choose Rust because my C is bad. So any excuse to stay where I'm happy and familiar. But yeah, good question. Borderline.
Yeah, thanks for the talk. It was pretty informative. I was looking online like a few weeks ago, and I saw that I was looking specifically on like IO Uring, and I knew that like IO Uring doesn't work too well with Tokyo. But then I also was seeing that there was some work on like a different async library called like comp.io, I think, that is completion based instead of the polling based that Tokyo does. And they were trying to work on like getting IOU ring working in like an asynchronous context. So I wonder if that's possible. I also think comp.io is relatively new, so probably not the best thing to look into at the moment until it's more featured. But I know also that there was a library, I think it was called like Apache Iggy, that recently decided to switch from Tokyo to comp.io. So maybe that would be something interesting if anyone wanted to like further push the boundaries on this. But yeah.
Yeah, so I've seen Compo, and it's also there's also Glomio, which is a similar kind of thing, and I think they're both originally based on C Star, which is a something similar but for C. I have no idea how well those work. I didn't try them. I wonder. So like in this case, we're kind of yeah.
Yeah, I was wondering too, because I haven't spent too much time looking into it. Just saw that it was possible.
In theory, it's just like you're just switching out Tokyo for Compio, right? Compio. It should be an easy change. I guess that's an exercise for the reader. You guys can go home and try swapping Tokyo for Compio. I sort of doubt that it's going to magically go from 4 gigabits to 147 though. But yeah, I'd love to be wrong about that.
On that note, this is probably silly, but like I wonder how Tokyo would perform if you just spawn blocking, which it has support for, where it'll create a thread instead, and then you can use blocking calls, and then you could still use Tokyo and do all your other Tokyo things, whatever it is that your application is doing, and then just use.
And you're saying use like embed that IOU ring sort of run loop on one of those Tokyo blocking threads.
Exactly, yeah. And then you could still like have other things waiting on certain things and like use the other async. I think.
Yeah, it sounds like it might work. Sounds like it might be a recipe for like crazy bugs. I'm not sure.
Yeah, well.
I can't think of any reason why it wouldn't work though.
Anyone else that I didn't catch have any other questions? Okay, you're not off the hook. I get to interview you now.
Okay.
This is the best part. All right. I've prepared a couple of questions to make sure I don't forget to ask anything. So the first thing is, I don't think you're from Tokyo, which is where we all live. Well, most of us. So what's your story and how did you end up here in Tokyo from, I guess, the United Kingdom?
From the UK, yeah, via Switzerland. Yeah, the startup I was working for in Switzerland went bankrupt, as startups do. And I was looking for a new job. Got an internship here in Tokyo for 6 months. Thought that would be interesting. And then extended it for another 6 months and then another year. And that was 10 years ago. I'm still there. Yeah.
And on that note of just like your story, Rust is, I think it's a little older than 10 years now, but I think we hit 1.0 like 11 years ago. But I think you've been programming maybe a little longer than that. So what's your story? How did you come to Rust? And why do you choose to continue to use it over C? I'm getting over whatever else for whatever projects you're working on.
Well, yeah. So I came from, I guess some people come sort of from the low-level languages up to Rust from below, and some people come in from the high. I'm coming from Haskell. Rust was originally pitched to me as C++ if it had been designed by Haskellers, which I think is not, not inaccurate. I guess Graydon is a Haskell fan. And that was an appealing pitch for us as a company that does high frequency trading at the time using exclusively Haskell, which is a great language, but is hard to reliably optimize. So Rust, I guess the prospect was similarly nice a language as Haskell, but kind of reliably optimizable. Like, you're not going to upgrade the compiler and suddenly the kind of deck of cards you have stacked to make the compiler optimizations catch suddenly it doesn't work anymore and you don't know why.
Interesting.
Yes,
Yeah.
Yeah.
I don't know. Go ahead.
But my story of programming, I started with QBasic in, I don't know, like 2002 or something. I came home from, I had just got my first laptop. I was very excited. I had Windows ME or XP on it. And I got home from school and my uncle was in the house and he said, "Alex, I fixed your laptop." And I said, "Oh, what was wrong with it?" And he said, "It had Windows on it." I booted it, and it booted into FreeBSD with, with XF86 and TWM as the window manager. And he'd been kind enough to give me Doom and Tux Racer. But yeah, basically the only fun thing to do on it was program. So
The funnest thing.
yeah.
That's pretty great, actually. I actually really envy you. My first programming language was when I was in middle school.
Okay.
And it was C++. So it took me quite a long time to learn to program. I didn't pick it up
Unbelievable
again until
trauma.
college. Yeah. That language is horrible. I'm sorry. Okay, so two more, and then I'll let you go. What is your favorite feature of the Rust programming language, either new or old? And why do you like it? Especially coming from high-level languages like Haskell, you must have an interesting take potentially.
Okay, well, coming from Haskell, I guess Rust, like, it's a step down in terms of language features, but this isn't a feature per se, but crates.io is way better than Hackage. Like, if you want a library that does something in Rust, you've got a good chance of finding something good. Hackage is like a ghost town, sparsely populated by terrible quality libraries. It's just, there's not that many Haskell programmers. Yeah. So that's really nice, being able to reuse other people's work.
Is great. I love programming, but I hate programming not the thing I'm trying to program. So it's pretty nice. Okay, last question. We have a lot of varying topics at Tokyo Rust. In the last few months, we've had a contributor to Cargo talk about how Cargo works and how they're trying to speed it up. We've had Mate, the last president, talk about his specifications crate that he's working on. Now we've had this really interesting systems programming, kind of refreshing systems programming talk about how you can do this. This is insane. What topics would you like to see next?
I recently switched Compositor to NIRI. It's pretty nice. It's written in Rust. I guess a talk about how NIRI works might be interesting. Like, I guess it's probably using a bunch of interesting kernel tricks. Probably uses memfds for communicating with clients, Wayland clients.
That's actually would be really interesting, especially given that, does it run in Wayland or in?
It's Wayland, yeah.
Okay, yeah, that'd be really fascinating. I personally have done a little bit of Wayland when I used to work at Google on Chrome OS. So it's really interesting, actually. There definitely is memory file descriptors and all this stuff floating around when you do that. So I will add him on, or her, or them on the YouTube that we upload and see if we can get them to
very-
come. Yeah, I'll just
wow.
probably, please come and give us a
Yeah.
talk. Or maybe they live here. We don't know.
Yeah.
That's it for me. So thank you very much, Alex. That was a really enlightening talk. And that's it for today in terms of the talk, but we still have this space for a little while. What time is it? It is 2023. So I'd say we should all plan to definitely be completely out of here by 21, which is 9 p.m. for those of you who don't do the 24-hour thing. Thank you so much for coming, and we'll see you hopefully sometime around the mid to end of March, probably maybe a little later end because there's the other talk on burn. So hopefully, bye recording.